Hi, welcome to this module. As you already know, Dr. Mahesh has been discussing on various aspects of neuroscience, including how the anatomy of a brain is, what are the EEG signals, and how we can use those signals for several applications, right. I will be taking few lectures, right, as a you can consider me as a TA for this course. So, what we need to learn in terms of instrumentation or in terms of designing electronic modules, and why these electronic modules are required when we talk about neuroscience, and when you talk about neuroscience, that means you are talking about acquiring signal from brain, right. Either it is EEG, which is electroencephalogram, where you take the or you record the neural activity through the scalp, this is the scalp, right, or you understand what is going on inside your brain by recording ECOG, which is called electrocardiography. What is electrocardiography? Electrocardiography is when the skull is open and you are placing a chip on the brain to acquire the signal directly from the brain is called ECOG. Now, having said that, let us see how we can use the fabrication or microfabrication for developing or designing these electrodes, which can either be used for EEG or it can be used for measuring ECOG. So, we will be discussing in this module the microfabrication, what kind of sensors we can design with microfabrication, including an example of EEG, and we will be looking at the anatomy of a brain as a video as the end of this particular module. So, if you see the slide, I will be talking about. So, I am a professor here in biomedical and electronics engineering laboratory. I head this laboratory and I also head the advanced micro system and biomedical device facility for clinical research. I work with Department of Electronic Systems Engineering, which is in the division of EECS at Indian Institute of Science, Bangalore. So, like I said, I will be helping to cover the instrumentation part of this particular course, and when we talk about instrumentation, we definitely want to see how we can fabricate the electrodes. So, we will be talking about what kind of facilities you require to fabricate electrodes, and when we talk about electrodes, we will talk about the micro and nano technology that can be used to design such electrodes. Now, what you see in this particular slide, like I said, I am heading 3 different laboratories, 2 laboratories, some photograph and images are shown here. The slide shows multiple photographs. If you see the one on the left, this one, this is a gowning procedure, or after a person gowns, before he or she enters into the lab, it looks like this. So, what are the different PPEs? PPEs is called personal protective equipment. One is, you start from the head, there is a cap. Second, safety glasses. Third, hood. Fourth, face mask. Fifth, gloves. Sixth, coveralls, that means this whole gown, coveralls. Seventh, boots. 8 shoe cover which are under the boots. You can see here, right. So, why to cover like this? Are there bacteria inside the lab? Are there viruses inside the lab? No, it is a clean room, right. So, what are we protecting from? What are we protecting ourselves from the equipment? No, we are protecting the environment, that means the clean room environment within the laboratory, because humans in this clean room are the source of contaminants. So, what do you mean by that? So, if you have ever tried, I am sure that you may have tried already, to see how your thumb tastes. Have you tried? If not, try it, and you will see that it is salty. So, what is the reason of this taste? Because there is NaCl, right. Same way there are other contaminants in our hands. So, if I touch the wafer, what is this wafer? It is a silicon wafer. What is silicon? We will look at in the slides. If I touch the wafer, this contaminants from my hand will transfer onto the wafer, and this will kill lot of chips during fabrication. Additionally, to avoid falling of hair, avoid any contaminant from your shoes entering the laboratory, avoid any beard hair falling into the lab. When you sneeze, it should not contaminate the wafer, and overall to protect and to conserve the environment within the lab, so that the silicon wafer or the substrate are not affected with the contaminants. Thus, it is very important to wear this particular gown along with PPEs. It is called lab gown, is also called coveralls, right, and this is used when a person wants to work inside a clean room or a nano fabrication facility, right. Having said that, I will be talking about some of the equipment within the facility, but let us look at the slide, and some of the equipment that we have in our department in my lab are shown in the slide. So, if you can see the slide, this one is called thermal evaporation, and it is also combined with electron beam evaporation. Now, we will discuss what is thermal evaporation, we will also discuss what is electron beam evaporation. Both comes under PVD technique. What is PVD? Physical vapor deposition, physical vapor deposition. What is physical vapor deposition? We use this technique to deposit a thin film of metal, semiconductor or insulator onto the substrate. We will discuss this technique in detail at some point of time. Then what we have? We have a oxygen bonding system or oxygen plasma system. What is this used for? This is used for bonding silicon with glass, or is used for bonding PDMS with glass, PDMS with glass. Okay. This process is called anodic bonding or oxygen plasma bonding. Two different stuff. Anodic bonding is when you bond silicon with glass, and oxygen plasma bonding is used when you want to bond PDMS with glass. The PDMS with glass is used for several applications, and one of those is for microfluidic devices. Now, if you know the fabrication techniques, if you know the process, and if you know the equipment, you can design several electrodes, several devices, several sensors, and our focus would be sensors that can be used for understanding or capturing the signal from the brain. So, if you see the next one, this is the fume hood. Fume hood is used in photolithography technique. We will be discussing photolithography at some point of time. What you see here is a micro manipulator, and the use of micro manipulator is to indent a tissue. What you see, this one is a HEPA filter, HEPA, HEPA, high efficiency particulate air. These filters are used for filtering out the particles in the lab and to maintain or to conserve the environment within the laboratory. Depending on whether it is class 10 or class 100 or class 1000 or class 10,000, the number of HEPA filters would increase. This is a workbench, and you can see here there is a nitrogen cylinder. Finally, this is the science side of the lab, where we can do lot of experiments. When it comes to using wet electrodes, we can use gel and use the electrodes. If you want to do some experiments, we can use this part of the laboratory. Anyway, this is just to show it to you that we require some kind of lab with a certain standard to perform all these experiments. Now, we already have seen a fume hood, we have seen a thermal e-beam evaporator. Now, what we will do is we will actually show you how to operate this particular system and how to operate the fume hood, how to operate the oxygen plasma system, what is the use of lithography system and spin coater, and same way we have this system which is called which is used for holding the rat. Okay. So, is a stereotaxic equipment and is used for holding the rat, and then we can perform experiments with rat. Our focus again is to understand the ECOG signals from rat's brain. We will see, if time permits, we will also show you how to operate this particular system. So, the point that I was making is that if you have a laboratory equipped with several facilities, you can not only design and develop the sensor, but you can also perform the experiment within the same clean room area. Now, one thing when you talk about microfabrication is etching. And what is etching? Etching is to remove the substrate, remove the part of the substrate. What is substrate? Substrate is a material on which you will be depositing or growing or developing a sensor, transducer or any device per se. So, if I want to etch the substrate, if I want to remove some part of the substrate, there are two techniques. One is called wet etching and one is called dry etching. Okay. So, now in wet etching, there are two hoods that are used or wet benches that are used. One is for acid and one is for solvents. We cannot mix acid with solvent and vice versa. So, if you see this slide, you can see here we have a solvent bench and we have the wet bench for using the acids. Alright. Now, these are some of the things that are there in the fab lab. There are many more things that we have in the lab, and we are going to talk about it in the experimental class, where we will show you how to operate several equipment and tools that we have with us in this department. You can see this is a BSL2 or biosafety level 2 hood, BSL2. There are several biosafety levels, BSL 1, 2, 3. 3 is generally used when you talk about virus. When you talk about viruses such as coronavirus, we need to use a BSL 3 facility. When you talk about bacteria, when you want to use cancerous tissues, bacteria, again you are talking about, let us say, E. coli or MRSA, then you can use BSL 2 facilities. Fortunately for measuring the signals from brain, we do not require biosafety hood. So, we do not have to worry about it. Then what you see is we have a microscope. So, I will show you how to use the microscope. This is particularly used when we will design a microchip that can be used for measuring the ECOG signal. We have a NI deck card. This is the signal conditioning, it will be used for capturing and acquiring the signals and to convert it to a required domain. That means that if I want to see how the sensor is performing, I can take help of the NI deck card and display it on a monitor. We have a oven with us. We will discuss about this, how it is useful, and finally you have a autoclave system. Autoclave is whenever you use any device, you need to autoclave it and then you have to discard it. That is a right procedure in the engineering, particularly when engineering is for medicine and other applications. Alright. So, having said that, of course, this is a anti-vibration table and this is the bio side of the laboratory that we have. We have a peristaltic pump, you can see here a peristaltic pump is there, and then we have a desiccator's microscope. This is a inverted microscope, and there is a difference. This is a stereo microscope. See, this one is a stereo microscope. This one that you can see my student working on this particular microscope, this is metallurgical microscope. Stereo, S-T-E-R-E-O, metallurgical. This is inverted. Okay. So, it can be inverted microscope, it can be metallurgical microscope, it can be stereo microscope. So, let us go to the next slide. This is nothing but say a 3D printing. You can see here 3D printing. Now, 3D printing is extremely important for developing the casing. We will be discussing about 3D printing in this particular in one of the modules for this course, and then we have some competition facility, which is right now we will not talk about that. So, let us see from the micro and nano perspective what exactly you mean by micro and why it is important when we talk about devices. Alright. So, one is that the surface to volume ratio increases when you talk about micro, and in particular when you talk about the gas sensing. But at the same time, when you talk about getting the signals, acquiring signals from cell, a single cell, right, it can be a glial cells, it can be a neural cells. So, in that case you have to fabricate a device which is micro in dimension, because you only want to get the signal from a single cell, and single cell can be somewhere around 5 to 10 microns, not big than that, some are really small. So, how can you capture the signal from a single cell? In that case you require to fabricate a device that can be used for such applications. At the same time, if you want to also deposit a metal layer to understand or to capture the signal from the scalp, which is your EEG signal, then you need to deposit a metal which is of few microns thick. So, when we talk about microns or nanometer, what exactly you mean when it comes to unit, right. So, this slide shows that if you talk about micron, 1 micron is close to 10 raised to minus 6. In fact, it is not close to, it is exactly 10 raised to minus 6 in terms of unit, where 1 nanometer will be 10 to the power minus 9, right. So, if in definition we say micro meaning 1 millionth and nano meaning 1 billionth. What are the use? Several applications: molecular manufacturing, nanotubes which can be used for building advanced lightweight materials as well as advancements in LCD technologies, several applications in the area of medicine, nanocomposites, electronics. If you already know what are the CMOS techniques or CMOS transistors, and particularly useful when we fabricate these transistors using e-beam lithography technique. Now, focus is not on the fabrication of transistors, focus is more towards our neuro instrumentation, right. But when you say instrumentation, that means it is a system, and system consists right from the sensor to the electronic module to the application and acquiring the signal and displaying it on a monitor, so that a clinician can understand the change in the brain waves if a person is suffering from certain disease. Now, what kind of diseases can be there? There can be stroke, there can be epilepsy, and there can be hearing problem, right. So, all this and there are many. When you talk about brain is the most complex thing to study, right. We know a lot of things about heart, how it functions, we know a lot of things about the our muscle activities, how it functions. When it comes to brain, there is still a lot of gaps and lot of science and engineering required to study brain parameters. We here along with Dr. Mahesh are working on several applications when it comes to brain, right from EEG signals to neonatal hearing to understanding the attention of a person working in the lab. Also we are working on developing ECOG chips. The chips can be measured, can be used for measuring ECOG, and these chips are bioresorbable. That means it is made up of material that once you implant in the body, it will dissolve. It is not just biocompatible. When you implant it, lot of things that you see are biocompatible, but when you to retrieve it or retract it back, it causes trauma to the patient. So, we are working on a chip that you can implant and it will dissolve in the body, because it consists of bioresorbable materials. We are working on that. We are also working on a stroke model, we are working on an epilepsy model, and thus this course is a two-part course. The first focus would be on introductory part, and maybe in the next semester we will talk about the advanced part. All right. So, let us go to the next slide, and when you talk about how large is a micron, then you can see from the slide that a strand of human hair, one single strand is around 50 to 70 microns. Okay. Now, when we talk about reg width, which a width is about 17 to 23 microns. When you talk about pollen is 30 to 50 microns. Dust mites around 10 microns, while what we are talking about is 1 micron. You can see compared to all this is 1 micron, the white spot. Right. This is the how large is a micron. You can just imagine that this is what we are talking about, and we are not just talking about micron, we are also talking about the nanotechnology. Now, let us quickly see what are ICs, because we will be using electronic modules for capturing the brain signals and processing it further. So, when you talk about integrated circuit or ICs, we talk about substrates. Substrates can be silicon. Substrate, what is substrate? Let me give you an example. Okay. So, let us say you want to deposit a metal. Okay. You want to deposit, let us say, aluminum on a substrate. So, what is a substrate? Substrate can be silicon, substrate can be glass, substrate can be polymer. Now, if I deposit aluminum directly on silicon like this, same way I deposit aluminum on glass and I deposit aluminum on polymer, then the metal that is deposited on a material like silicon, glass or polymer, then in this case silicon, glass and polymer becomes the substrate. In this example, silicon, glass and polymer are the substrate, because it is a base material on which you are depositing metal. Now, this is an example of metal. You can also deposit semiconductor on semiconductor. You can deposit insulator on semiconductor. For example, instead of aluminum on silicon, we can deposit silicon dioxide on silicon. Still silicon will be your substrate. Silicon dioxide is a material grown or deposited onto the substrate. Now, in microelectronics industry or in microelectronic chips, semiconductor materials are used as a substrate. So, can you tell me which one is semiconductor? Polysilicon is polymer is semiconductor? No. Glass? No. Silicon? Yes, right. So, when you see the integrated circuit, you will find that more than 95% of the semiconductor devices fabricated, silicon is a leading semiconductor material. Okay. And the question comes as how can we fabricate a silicon substrate, or how can we develop a silicon wafer. Then for that we have 4 different steps. The first step is production of electronic grade material. Second, so this electronic grade material is developed, or grade silicon, production of electronic grade silicon. Silicon is produced from silicon dioxide. Now, what is silicon dioxide? Silicon dioxide is sand, right, is sand. There are 2 techniques for developing the electronic grade silicon. One is called Czochralski technique, another is called float zone technique, right, and we will see both the techniques. Now, having said that, this is our first step. Second step is crystal growing, third step is polishing of silicon crystal, and fourth step is slicing of silicon wafers. So, we will see each step in some slides. When you finish all 4 basic steps, what you get is a silicon substrate. Now, I am drawing a cross section of the silicon wafer. Okay. Silicon wafer looks like this. There is a reason of having this flat, we call as a primary flat. All right. In some cases you will see that there is a secondary flat here, and the reason of having primary flat and secondary flat I will discuss in few slides. So, before moving to discussing about silicon wafer, how it is, how we can know whether it is 100 or it is 111 or it is 110, right. What are the crystal planes or orientation? Before we go to that particular topic, let us see, if you take an IC, right, and on removing this black box, if you ever tried, do not try without a proper supervision, all right. It is not advisable, but if we remove this box, then what we can see is a chip that is mounted on the substrate, and this chip has billions of transistors and the substrate is silicon, while the connections or the contacts to the external leads, these are external leads, are using the wire bonding. So, wire bonding is a technique of connecting the external leads with the contact pads, and it is used for generally in the silicon chip. So, what are the size of silicon wafers that are available? We have a 2-inch wafer, then we have a 3-inch wafer, 4, 5, 6, 8, 12, 18. What is the advantage of having a wafer which is of larger diameter? The advantage of having wafer of larger diameter is that we can integrate lot of transistors simultaneously. So, for example, if I can have 1,000,000 transistors, 1,000,000 transistors in 2-inch wafer, then you understand that in 18-inch wafer you can have how many, right. So, that is the advantage of using the larger substrate. Most of the laboratories where they use the wafer in academics, they restrict themselves to 6-inch wafer, okay, where industry tries to go for 18 and 12-inch wafer, even larger diameters. So, this is the scenario. What are the applications of silicon wafer? See, from an infrastructure point of view, there are industry standards that chip manufacturer has to obey. There are production tools, utilities, material, chemicals, meteorological tools. Meteorology is to understand the properties of the material. It can be SEM. SEM is called scanning electron microscopy. It can be TEM called transmission electron microscopy. It can be XRD called X-ray diffractogram. It can be AFM called atomic force microscopy, and that there are many more UVVs, UV visible technique. Then there is FTIR, right, Fourier transform infrared rays, and many more. So, then there are analytical laboratories, then technical workforce, and finally, they supply to college and universities. When it comes to consumers, the computers, automotive, aerospace, medical, and lot of other industries, they use the silicon chip. Customer service, original equipment manufacturers, PCB manufacturers have the usage of the silicon wafers exclusively. Now, we were talking about the manufacturing or developing a silicon wafer, which you can see here, silicon wafer from sand. So, first you take a sand, extract polysilicon, and you this polysilicon you heat in a crucible. This crucible is at extremely high temperature, so that it will melt the polysilicon. Then you insert this seed crystal, it is a seed crystal like this, you insert it into this crucible, and crucible has the molten polysilicon, right. When you insert it down like this, okay, insert it down and you rotate it. So, this seed crystal, let us say, rotates in the anti-clockwise direction, then the crucible will rotate in a clockwise direction. So, it is opposite to each other. Seed crystal will rotate in a anti-clockwise, then crucible will rotate in a clockwise direction, and slowly you need to pull out the seed crystal. You need to pull out the seed crystal, because seed crystal is at lower temperature compared to the molten polysilicon. What will happen? The crystal will start the silicon crystal will start forming across the seed, and you will be able to achieve a single crystal ingot. I will show you a video, so that it becomes easier for you to see how this is this can be done. This is just to make you understand that what are the procedure, or what is the procedure to obtain the silicon wafer that we use as a substrate for semiconductor industries, for manufacturing microelectronics chips, as well as for lot of devices related to not only sensors and other domain, but also for developing several chips for instrumentation which is used in neuroscience. Okay. So, single crystal ingot, then you have to trim. So, these sides are trimmed. Next one is you grind it. This is grinding, right. Why? What is the reason of grinding? The reason of grinding is to obtain a flat. What is the use of flat? I will show you in a few slides. Finally, after you grind it, what you do is you slice the wafer. All right. After slicing, this slicing is done with the help of a diamond wire or diamond cutter. You do the edge rounding. Edge rounding is done. After edge rounding, you perform lapping. Now, we need to make the wafer extremely smooth, right, all the way to 2 nanometer roughness, wafer etching, polishing and finally inspecting. So, these are the steps that are used right from crystal growth to ingot to trimming, flat grinding, wafer slicing, edge rounding, lapping, etching, polishing and inspection. Let us see what is the role of the primary flat, this flat grinding, you see flat grinding, what is a role and how it can be used to identify the crystal orientation and the type of the wafer. So, there are two types, you see if the silicon is not doped, okay, it is called intrinsic. If it is doped, what is doped? Doped means adding impurities. What are impurities? Impurities can be, if it is a silicon and if I add p type impurities, trivalent impurities, it becomes p type silicon. If I add n type of impurities, it becomes n type silicon, right, which is pentavalent impurities. So, how would I know looking at silicon whether it is p type or n type? The second question is, how would I know what is the orientation of the wafer? So, if you see this particular image or schematic, you will see that all these 4 different kind of wafers, of course, all of them are silicon wafers, they have primary flat. You see, I write primary flat, we let us say PF. Okay. So, this wafer also has primary flat, this wafer also has primary flat, primary flat and same with this wafer as well, right. Now, you see, is there another flat in this wafer? No flat, right. So, the if you have a secondary flat, SECONDARY, secondary flat, let us call this as a SF. Does it has any SF? No. What about this wafer? Yes, SF is there. What about this wafer? Yes, SF which is secondary flat is there. In this case, yes, secondary flat is there, correct. So, we can see there is a primary flat, in one of the wafer there is no secondary flat, in remaining 3 types there is a secondary flat. Now, if the wafer is p type 111, there will be only primary flat and no secondary flat. Okay. If the wafer is p type 100, there will be secondary flat at 90 degree with respect to primary flat, right. See, this is at 90 degree with respect to primary flat, correct. Then if it is n type 111, then the secondary flat will be at 45 degree with respect to the primary flat, and if it is n type 100, then it is 180 degree with respect to the primary flat. The secondary flat is at 180 degree with respect to primary flat. So, depending on whether there is secondary flat or not, and if secondary flat is there, then with respect to primary flat, what is the angle of secondary flat will help us to determine the type of the wafer and the orientation of the wafer, alright. That is the use of primary flat in particular. So, when we do the when we fabricate the silicon wafer, we also fabricate a secondary flat with respect to the primary flat. Now, so that means silicon is a substrate. What can be other substrate? Glass. So, if you see the slide, what you will see is that we have used glass in this case as a substrate. We can also use polymer as a substrate, right. So, silicon silicon, glass, polymer, can be PDMS, and this is just an example of a cantilever fabricated using silicon. All right. So, let us finish this module on this particular slide, and we will understand more about the microfabrication, some of the techniques in the next module. If you have any questions, always you are free to ask through the forum, right. TAs Dr. Mahesh and I, we all will try to answer your questions as soon as we can. Till then, you take care. I will see you in the next module.